Welcome to the instructional video for 2.2 in Math 30-1. And what we're doing in this particular lesson is we're going to look at the difference between a function, so just y equals f of x, and we'll talk about several different ones, although we tend not to make this too complex. What we're going to do in 2.2 is we're going to look at what happens when you take the square root of the function. Now, immediately, if you remember some of the stuff about square roots, which I hope you do, there is a pretty big, exception, or maybe not exception, but limit on what f of x can be, because f of x is inside a square root, and we're only going to do this with square roots, not cube roots or fourths or anything like that, then that means f of x has to be non-negative. So it has to be greater than or equal to 0. Where f of x is not greater than or equal to 0, the square root of f of x doesn't exist. Now, to try to make this just a little bit easier to work with, I'm going to make up a function now. So I'm going to make kind of the easiest function I can think of, maybe not easiest, but an easy function is f of x is equal to x squared. So our standard parabola. My other function then, what I'm going to do is I'm going to write it using function notation, and I'm going to say that function g of x is going to be the square root of function f. Now, that means that now I can say, g of x is the radical graph and f of x is just our, quadratic. Now, one of the most important things that I push again and again is mapping. So if we talk about points on f of x, I'm going to make them x comma y. So those are on the original. To get to the points, the corresponding point on g of x, what I'm going to do is I'm not going to touch the x, but I am going to end up taking the square root of the y value. And so I'm going to grab a couple points on f of x equals x squared. So let's look at the origin because it passes through that. Let's look at negative 1 comma 1. We'll look at positive 1 comma 1, and then we'll look at maybe 4 comma 16. That's a point on a parabola. There's lots of other ones, but I want to show you what happens here. So looking at where these points map to on g of x, 0 comma 0 is going to be 0 comma the square root of 0. Which is just 0 comma 0, right? That point didn't change, and that would be invariant in this case. Negative 1 comma 1 is going to turn into negative 1 comma the square root of 1, which is just negative 1 comma 1. 1 comma 1 will turn into 1 comma root 1. That's going to stay at 1 comma 1. And I hesitate to kind of choosing these points because you see 3 of these and it looks like it's not doing anything. But look what happens to 4 comma 16. 4 comma 16 becomes 4 comma the square root of 16, which is going to change into 4 comma 4, which is what root 16 is. Now, really importantly, when we do this, I have never seen a question that asks you to take the positive negative root. So we are just looking at the positive square root of a function, and the biggest thing that I want to push again and again and again is certainly the domain can change, but when you're actually taking the square root of a function, the x coordinate doesn't change in this operation. Right, I am literally just taking the square root of the original y value. Now, there is some pretty important concepts that this table kind of highlighted. G of x is equal to f of x, and I'm going to label this as invariant points. Okay, this is only true when g of x is the square root of f of x, but that's what we're dealing with on this list. G of x is equal to f of x when f of x is equal to positive 1 and when f of x is equal to 0. Now, one of these is actually pretty important. F of x is equal to 0 are the x-intercepts. And what that means is that whatever the x-intercepts of f of x are will also be the x-intercepts of g of x. Being able to identify invariant points is a big benefit when you're doing something like this. I'm going to show you basically the visual of how we do this. I am going to graph both of these functions. I'll reiterate that f of x is equal to x squared. That's our classic parabola. I really think you probably have a good handle on that by now. And then g of x is identified as the square root of f of x. Now, don't get me wrong, I could write that g of x is equal to the square root of x squared, but then students are too tempted to just take the square root and say that it's equal to x, and it's not. And that's something that's going to be really important, that taking the square root of a number is different than taking the square root of a function. Because ultimately what we're talking about is a transformation. And I'm going to plot those points that we identified. So 0, 0 is not going to change. 1 comma 1 and negative 1 comma 1 aren't going to change. But then this point somewhere up here, and I'm just going to write 4 comma 16 up there. I should have done in black, but that's okay. That's going to track down to 4 comma 4. Now, what happens with this function is something a little bit maybe not unique, that the function, the square root of the function, so g of x, is actually going to be above f of x initially, and then below f of x for the rest, and it's going to exist on both sides. Now, unfortunately, we have to get into a little more detail here. What's happening here is that f of x is greater than 0, but less than 1, which means that the square root of f of x will be greater than f of x. And I would encourage you that if you have your calculator, check if the square root of 0.81 is greater than 0.81. And if you do have your calculator, the square root of 0.81 is 0.9. And 0.9 is definitely greater than 0.81. We'll look at one more number here. What about the square root of 0.25? Is that greater than 0.25? If you have your calculator, the square root of 0.25 is 0.5, and that's definitely greater than 0.25. So we have to remember that when f of x is in between 1 and 0, not including 1 and 0 because they're equal at that point, but if f of x is in between 0 and 1, then the square root of that function is above. And I want to maybe write that in words, that root f of x is above, which is really what greater than means, f of x. And we're going to talk about that. Now, the other side of this, and I'll do it maybe from here to basically infinity, if f of x is greater than 1, then the square root of f of x will be less than the original function. And we can see that on the graph, right? These two graphs are equal when x is -1, 0, and +1. When the function itself is above 1, so that's from this point with a round dot and on, we see that the red graph is below the black graph. And we're going to see that in more detail as we go through the examples, but it's going to be pretty important that if you're doing this manually or based off a graph, it's really useful to know when the invariant points happen and when the radical is above the original and vice versa. And we'll examine that in the examples to follow.